Systems of equations. A look at 2x2 systems. So our learning objectives for this lesson are, number one, what is a system of equations? So how do we define a system of equations? Number two is, what is a solution to a system of equations? 3. Solving a system of equations by graphing. So graphing is one technique to solve a system, and we'll look at how to solve a system by graphing. The fourth objective is to solve a system of equations by substitution, yet another method to solve a system. The last objective is learning how to solve a system of equations by elimination, or the addition method. They're synonymous. Sometimes we'll call it elimination, sometimes we'll call it addition, and we'll talk about that more as we learn that objective. Okay, so these are examples of systems of equations. Let's examine both examples carefully. Notice both systems have two equations listed. So here we have a system. We have two equations. So let's call this equation 1 and equation 2. Okay, so notice that we have two equations. And what type of equations are these? They are linear equations. Okay, so these are just graphs of lines. Now there are examples of systems of equations that are nonlinear, but those will be talked about in college algebra. Here we also have a system of equations, and both of these equations are also linear. It's just that in this one, the top equation is solved for y. Okay, so instead of the x being on the left-hand side with the y, it's specifically solved for y. And the second equation is in a form very similar to this first equation. So what is a solution to a system of equations? We looked at a system of equations and we said that they were both equations that had x's and y's in them. So a solution to a system of equations is an ordered pair. So it's an x and a y value that makes both the equations true. Okay, so that's important. It can't just make one of the equations true, it has to make both of the equations true. Okay, so here we want to determine if -5, -6 is a solution to the following system of equations. So let's examine that. Now, this is the graph of a line. Okay, I mean this is the equation of a line. So here in this equation there are infinitely many x and y points, or x and y coordinates. There are infinitely many ordered pairs that will work for this equation. Okay, because anytime we have a point on a graph, that point represents an x and y value that when it's plugged into that equation, it will work. Okay, so here we have an equation and another equation. So this point has to work in both equations at the same time. So to determine if it is a solution, let's take the top equation and let's plug the x value in for x, and let's plug the y value in for y. So let's check this. 2 times -5 is going to be -10, minus a -6 is going to become +6, because a negative times a negative is a positive. And so then this is -4. Is that true? Is -10 plus 6 -4? It is. So then that works. Okay, but we're not done. We have to check it in the second equation also, because all we've found so far is that this ordered pair, -5, -6, will work in the first equation. But it has to work in both equations to be a solution to the system. So if we plug it in here, Okay, then this is going to be negative 15 plus 30 is 15. Is that true? If we add these, we get 15, and 15 does equal 15. So that's a true statement. So then that means that this ordered pair is indeed a solution to this system of equations. Okay, so also we want to note that a system of equations that has one point as a solution is called a consistent system. Okay, it's a consistent system. Sometimes you can have not just one solution will work, but in fact infinitely many solutions to a system of equations. Also, you can have a situation where you have no solutions to a system of equations. So we'll talk about that more as we go through in a moment. Okay, so here we have a system, and our directions are to graph the system of equations. So let's graph this system. So this is the graph of a line, and it's already in y equals mx plus b form. So let's take this and let's plug it in. So we have y equals negative x minus 1, so negative 1 is our y-intercept. And then negative 1 is also the slope, because when it's written in y equals mx plus b form, remember b is the y-intercept, so that was negative 1, so that's our y-intercept. M is our slope. Well, here m is negative 1, right? So that means that our slope, remember, is our rise over our run. So we're rising negative 1 when we run 1. So that means from here I'm going to rise negative 1, which means I'm going to fall 1, and then I'm going to run 1. Okay? So if I run a positive value, remember, I'm going to go to the right. If I run a negative value, then I'm going to go to the left. If I'm supposed to rise a negative value, then that means down. Rising a positive value means actually rising, so rising up. So from here I'm going to rise negative 1, which means I'm going to fall 1, and I'm going to run 1. Okay, and so from any point on the line you can always do that and get as many points as you want. And so now if we extend this line through, I don't have a ruler, but that's good enough. Good enough. Okay, so then this will be our line, sort of. I mean, I don't have a ruler, but okay, so we need to graph the other line. We've graphed equation 1. We need to graph equation 2. Now, you can choose however you want to do this. You can take this equation, equation 2, and you can put it in y equals mx plus b form and graph it the same way that we did this one. Okay, you can do that. You just move this over. You'd have to divide by negative 3, and you would get some fractions. That's totally fine. But it's not necessary. Okay, so one thing that you could do is you can just try to find a couple of points on the graph. How could you do that? By picking points and plugging in. So oftentimes easy points to choose right off the bat would be like x and y intercepts. So remember, to find the x-intercept, we're going to make y equal to 0. Okay, so if we make y 0, we want to find the x value associated with that. So if y is 0, then this is negative 3 times 0. So this would be 4x minus 3 times 0 is equal to 24. So remember, this is just 0, so that's gone. So we have 4x is equal to 24. And if we divide by 4, we're going to get x is equal to 6. So that means our x value would be 6. Okay, so now if I want to find, say, the y-intercept, then I'm going to make x equal to 0. So I'm going to do the same thing, except this is going to be 4 times 0, so that's going to be 0. Okay, we're going to have negative 3y is equal to 24. Remember, this is going to be gone. So we'd have negative 3y is equal to 24, and if we divide by negative 3, we get y is equal to negative 8. Okay, and so here these are 2 points that are on this graph. Okay, 6, 0. Okay, remember, just think of these as ordered pairs, right? This is like the ordered pair 6, comma 0, and this is the ordered pair 0, comma negative 8. So this is 0, negative 8. And so now all we have to do is just connect the dots. Okay, now if you have a ruler, like I said, it's going to be a lot easier. I don't have one, but I think it's going to be like about like here. I think this is going to be another point. I think that should be our solution. Like I said, I don't have a ruler, but that's good enough. That's the only thing about this method is for it to work, it needs to be kind of precise. So if you're going to just draw it by hand, you should probably use some sort of a straight edge so that you can tell what you're doing. Okay, so the point to where they touch, okay, so the point where the lines intersect is going to be our solution. So remember, x is going to mark the spot, okay, where they intersect. That's going to be our solution. So our solution is going to be 3, -4. So our solution should be 3, -4. How did I get that? Because that is the ordered pair for this point. I start off at the origin, I go 3, and then I go down 4. So that's going to be 3, -4. So that should be our solution to this system of equations. Okay, and this is a graphing method. Now, since we've seen the graph, we know that these are lines and they intersect in one point. But let's ask ourselves, with lines, what other kind of scenarios could we have? Okay, two lines, it seems like will always intersect in one point, but is that really the case? Let's think about that.